Alright everyone, these are the notes um, for March 23rd. So, you know, before spring break, and when we were going to come back from spring break, we were going to continue our discussion with limits of multivariate functions, but, that's obviously things have been preempted because of this whole thing, but so I kind of talked about how we were going to do these things, or how we looked at one example of this, if you recall. I know that was a while ago. That was before last week, so you might want to refresh your memory on how we evaluate limits of multivariate functions, but I was going to continue with some more examples of that now. So basically the idea behind finding the limit so this is something we did talk about, but I want you to recall it anyway. So when we're finding limits of multivariate functions, the idea comes from it comes from the following. I need to pick different ways to approach a given point and when I say different ways, I mean plural. So I want to go different ways to approach a given point to show that the limit or the function evaluates to different values. So that's the idea behind finding the limit of a multivariate function. If you're approaching 0, 0, and you get it to go to one value, and then you approach 0, 0 on a different curve, and you get it to go to a different value, then you've shown the limit doesn't exist. But otherwise, if you plug in the limit and you get a number, that's it. That's the value of the limit. I did show a few examples of that before we left for spring break. And I did show an example of where, we got an undefined limit. So I'm going to keep going with that. I'm going to show you another example. So compute. The limit as the ordered pair x comma y approaches 0, 0 of 3x to the 4th times y all over x to the 8th plus y squared. Okay, so how are we going to do this? Well, so I ask you to compute that multivariate limit. Well, if I just plug in 0, 0 in here, what do I get? So if I sub 0, 0 in for x, y in here, what do I get? Well, that's easy. If I put in 0, 0, I'm going to get 0 over 0. Right? This is not 1. This is not 0. You should know that by now. This is called and you've seen it from Calc 2. This is called indeterminate form. You've also seen it in Calc 1, but but what we can't do here that we could do in Calc 1 and Calc 2 was we cannot do L'Hopital's rule. So, in single variable calculus, whenever you get indeterminate form, right, you'd apply L'Hopital's rule and then evaluate the limit again and so on. But we can't do that here because this is a multivariate function. It's not single variable, so we can't do that here. So, well, what are we going to do here? So, I'll make a little subnote here, and I did kind of allude to this in the other example that we did prior to spring break, but generally when you get indeterminate form of a multivariate function limit, that generally implies, so generally 0 over 0 or indeterminate form implies that the limit of the multivariate function is undefined or does not exist, generally. So basically what this becomes is a problem where you have to show that this limit is undefined. So that's what this is hinting towards. You got to show that this limit is undefined. So how do we show, just to refresh your memory, how do we show a limit is undefined? We pick different ways to approach a given point to show that this evaluates to different values. So I'm approaching 0, 0 in the x and y direction. So I got to find, because this is in R3, I have to show that this function approaches this point from all different directions in space, right? And I have to show that, if I could show just 2 different values for that, then I've shown that the limit is undefined. I just need 2. All right, so so here we go. To show limit is undefined. So here we're going to do this. So I'm going to approach zero comma 0 along a line and along a curve. It doesn't matter along whatever, like a line, a curve, it doesn't matter. Just as long as you approach 0, 0 from x and y. So you want to, basically the idea here is you want to hold one of these variables constant. You want to hold one of them at the value that it is. And you want to approach 0 on the other one along a line, a curve, or whatever. So let's just try one. So I'm going to try the line y equals 0 first. So that means I'm going to approach zero, 0 along y equals 0. So basically what I'm saying here, the y coordinate is 0 and x is approaching 0. That's you know, that's, so what line is this? You know, what line is y equal to 0? That's the x-axis, right? So I'm approaching along the x-axis, and I'm converging towards the origin on the x-axis. Basically, that's what this is saying. Excuse me. So if I plug this into my limit, right, I'm letting y equal 0, and I'm approaching this. So I'm approaching 0, so that means that x is approaching 0 as y is equal to 0. That's what it means. So I'm going to take these values, and you know, basically these are treated the same way, like y is 0, but I'm saying x is getting to 0, so we're going to treat x as 0 anyway. So I'm going to plug these in here, into here, and see what I get. So when I do that, here's my function. So plug them in. So, all right, well, so so I have 3 times x to the 4th times 0. So y is being 0, right? Y is 0. Y is equal to 0. So just plug in 0 for y. So when I do that, I'm going to get 3 times x to the 4th times 0 in the numerator. And I'm going to get x to the 8th plus 0 squared in the denominator. So when I do that now, I'm just going to have a single variable limit. So now I'm going to have the limit as x approaches 0, right? Because now y, like I said, y is now 0 of this expression. So that expression is 0 over x to the 8th, right? Well, what does this go to? Now we're at a single variable limit, which is easy. This is just 0. Okay. Well, that's, remember how I said we need 2 different ways. So this is one way. Now I have to compare this to another way of approaching 0, 0. And if I get a different value for that, then I've shown the limit is undefined. All right, so here's where things can get a little tricky. And it's not that it's hard, it's just, it could be a little unclear. But when you're evaluating the limit here, you want to think of all the different possible ways you could approach. Well, you don't want to think about all of them, but you want to think of a few different ways you could approach 0, 0, right? So if you do a little thinking about that, right? So how many ways, or well, there's an infinite number of ways. So I just need to show 2 that are opposite values. Or, well, different values, I should say. Okay. Well, can I approach 0, 0 along, let's say, I'm thinking, so what about y equals x, right? So if y equals x, right? So let's just say this. Consider approaching 0, 0 along y equals x. I don't know if I'm going to use it, but I'm just considering it. I just want you to see that. So if y is equal to x, right, am I going to approach 0, 0 on that point? So if x is 0, that means y is 0 because they're equal to each other. Yeah, that'll work. So you could plug this in. You could, since we're assuming this, plug it in and see if you get a different value. But I want you to think of all different other kinds of ways that work as well. So can I approach along y equals x squared? Can I do that? Yeah. Y equals, this is a parabola, right? So, you know, if I put a little basic graph here, right? Y equals x, that's just, you know, that's an easy line, right? That's approaching 0, 0. This is x, and this is y, right? I know this is in R3, but I'm just trying to get you to see the value that it goes to 0, 0. And, you know, x squared, that's just a quadratic, right? That's a parabola. So, or a power function. So that does this, right? So, you know, they all approach the ordered pair 0, 0. So, yeah, any one of these variations is going to work. So you could try this one. You could go x to the third. That's still going to, and x to the fourth, and so on. So you could actually consider, in general, approaching 0, 0 along y equals x to the nth power, where n is a number, might work. I'm not saying they will all work, but, you know, in these kinds of problems, sometimes you just got to do trial and error. Try this, plug it in here, right? Y equals x, that means you could set y equal to x or x equal to y and then see what this evaluates to. Try this one. If I look at my original function, which is right here, right? I'm trying to get this thing to evaluate to something other than 0. So, you know, this is where you have to really think hard about your algebra, right? So if I look here, I have x to the fourth, right, times y. I have x to the eighth plus y squared. So I'm trying to get this to go to something else. Now the first time I did it, I got 0. Okay. So if I could get this, so because this was 0, the numerator became 0, right? So let me try and force the top here to not become 0. So how can I force the top to not become 0? So I don't want 0. In the numerator. So you want to pick y equals x to n so that the top does not become 0. That doesn't, you know, that's not the most straightforward, you know, this isn't very straightforward. You have to think about it a little bit. So what variation of this function, when I plug into the top, is going to get me something that won't be 0. So I don't want, you know, I want something that might cancel out down here. So let me think here. X to the second, if I plug in y equals x to the second, so I'll have x to the eighth plus x to the second. All right, well I'll have x to the fourth, right, because it'll be squared and squared again. But I can't add them together. Okay. And that's not going to, you know, I'll have x to the eighth plus x to the fourth, and I'll have x to the fourth up here. I could try that. That could work. I'm going to pick, so either one of these might be sufficient, but I'm going to pick So I'll just pick y equals x to the fourth to approach 0, 0. But I want you to realize something, that just because I'm picking this does not mean you can't pick x squared, x to the third, x to the fifth, or so on. The goal here is to pick something that I approach this value on this curve, excuse me, so that this simplifies to different values, all right, to a different value other than 0. So a lot of this is trial and error. Pick it. Let's try it. Okay. So the limit as x comma y approaches 0, 0 of 3x to the fourth y all over x to the eighth plus y squared. So because y is now equal to x to the fourth, I'm going to replace y with x to the fourth. So in the numerator, I'm going to get 3x to the fourth times x to the fourth all over x to the eighth plus, now y became x to the fourth, so this will be x to the fourth squared. So now when I go through that, so I'm still taking a limit, but I'm approaching, since y is now equal to x to the fourth, now x is going to be approaching 0 on that curve. So now the limit as x approaches 0, what do I have in the numerator now? 3x to the eighth. All over, so this is x to the eighth plus x to the eighth, right? Excuse me. Well, this is a single variable limit. This x to the eighth plus x to the eighth is 2x to the eighth. I think you could see that we're good here, right? What's going to happen to these x to the eighths? Obviously, they cancel out. Boom. So now what I have is, excuse me, is the limit as x approaches 0 of 3 halves. Hey, which is just 3 halves. Ta-da! So what does this mean? I approached 0, 0 along this curve, and I got, well, along the line y equals 0, which is still a curve, it's just a line. And I got 0. I approached 0, 0 along this curve, and I got 3 halves. Uh-oh! I got different values approaching the same point. So because of that, I've shown the limit does not exist. So, to summarize, since 3x to the fourth times y over x to the eighth plus y squared approaches different numbers, depending on how x comma y approaches 0, 0, the limit is undefined. That's it. You know, when you do this on, like, you know, if you do this by hand in your own, you know, once you've shown these two values for approaching the same point on a different, you know, on a different curve, and once you've shown the function evaluates at two different values, you're good. I just want to, I'm just being thorough with the problem. Okay. Man, my throat is raspy. So, you know, sometimes these things could be a little, you know, not so straightforward, but they're really not that bad. Sorry. Let's look at this one. So compute the limit of x comma y approaching 0, 0 of x squared times y squared all over x squared plus y squared by converting to polar coordinates. All right. So what are your polar coordinate conversion equations? You remember? So polar coordinates. So when you're doing these suckers, you know, this was covered to you in Calc 2. It should have been if you forgot about it by now. But x equals r cosine theta and y equals r sine theta. All right. And you also know that x squared plus y squared equals r squared. Right? Those are the conversion equations for polar coordinates. So since that's the case now, well, why don't we just plug these in to our function for x, y, and so on. So it seems pretty straightforward now, right? So just take this and replace them with x, y, and etc. So I have x squared times y squared. All right. So this numerator is going to become this quantity squared times this quantity squared. So I'm going to have r cosine theta quantity squared times r sine theta quantity squared all over. Now I just said down here, well, this is nice. X squared plus y squared, that is r squared. Beautiful. Then I'm going to go through that. You know, you could, if you didn't know this, like if you didn't know that, you could go through this. You'll get it by just plugging in this and this, and you'll get that wonderful identity. Sine squared plus cosine squared equals 1, and then you'll just get r squared times 1, which is obviously r squared. But because I know that now, I could just write r squared. So now when you go through the top, so this is going to be r squared times cosine squared theta, and r squared times sine squared theta all over r squared. So, well, if I look here, how many r squareds do I have? So, well, one of these r squareds is going to cancel out with the denominator's r squared. So that's, that's pretty straightforward. They cancel out. So now I have r squared times cosine squared theta times sine squared theta. Okay, so that's what I have now. So now that I have that, this is what, this is what I have. I just have, I have a function in terms of r and theta now. So the limit, so x is in terms of r and theta, and y is in terms of r and theta. So x and y now becomes the limit as r and theta. And that's approaching the same value, 0, 0, of this quantity. Well, that function, I should say. So that's what I have now. That's what I have. I could just replace this because those are the conversion formulas for polar and Cartesian coordinates. All right. So, well, if I plug in, plug in the value, see what you get. Well, you're going to get, so what's cosine at 0? Cosine of 0 is 1. Sine of 0 is 0. And r is going to be 0. So I'm going to have 0 times 1 times 0. Well, that's easy. You're just going to get, so if we just plug that in, you're going to get 0 squared times, so cosine of 0 is 1, so you're going to get 1 squared times 0 squared, which is obviously just 0. And that's fine. There's nothing wrong with that. There's nothing wrong with that. It's when you get undefined or indeterminate form that you have, then you got to show that this goes to two different values. All right, that one was pretty straightforward. Plug it in, you get a number, you're done. But if you get indeterminate form, you got to show it's undefined. That's the more, trickier way. Let's look at this one. Let's look at this one. So ooh, 3 variables. Oh man. So that's x squared plus y squared plus z squared all over 5y squared plus z squared. All right, well, first things first, if you plug these values in here, you're obviously going to get 0 plus 0 all over, you're going to get 0 plus 0 plus 0 all over 0 plus 0. That's going to give you indeterminate form. So, all right, well, so that should be pretty obvious. That's definitely going to go to that should be an equals sign. That's definitely going to go to 0 over 0, which is indeterminate form. All right, so now I have to show that this, is undefined. Okay, well, So now I'm not just considering 2 variables here, I'm considering 3 variables. So this one is in, you know, if I draw a coordinate system, right? This is in R3. So I'm approaching that point, right? I'm approaching 0, 0, 0. And I'm approaching that point in all different kinds of directions. Not just along the axis. I could, but, you know, in all different possible directions. I just got to find 2 directions that'll give me different values for that. So, the most basic way to try this is start with the, you know, as you saw in the previous examples, start with the axis lines. You know, the axis lines. So approach 0, 0, 0 along the x-axis, the y-axis, the z-axis. Any, you know, I just need 2 values. So you could try the x and y-axis, the x and z-axis, any combination of those 3. So here's what I'm going to do. I'm going to approach zero, 0, 0 along the line y equals z. How did I figure that out? Well, basically, this right here is just a variation of the, so if I'm going along the line y equals z, that means I'm in the yz plane. So that means x is going to be equal to 0. That's just the yz plane. And in the yz plane, x is equal to 0. So that means, you know, basically I'm in the plane of the sheet of paper. Right? This is 0, so I'm approaching that line. I'm approaching this line right here. That's the line y equals z. All right. So x is now equal to 0. So plug that in here, and then take the limit from there. So let's go. So I had the limit x comma y comma z 0, 0, 0 of my function. All right. So y is now equal to z. So and x is equal to 0. So I want to take those 2 pieces of information and replace them in here and then see what I get. So when I have that, so x is 0, so I'm going to have 0 squared, right? Plus now y is z, so this is going to become z squared plus z squared, right? Because that was still z, all over 5z squared plus z squared. So since the only variable I have left is z, now I'm just dealing with the limit as z approaches. Well, I'm approaching 0, 0, 0, so z is approaching 0 as well, of whatever this simplifies to. So I'm going to get 2z squared all over 6z squared, which is obviously 2/6 or 1/3. All right. Let's try another one. Let's try a different So we tried the YZ plane, right? Now let's try the XY plane. All right. So if I'm in the XY plane, well then the equation for the line that goes through the origin there is just, that's easy, y equals x. Or better yet, what I could do, actually, you know, let me rephrase what I was going to say. I'm sorry. It's not that I can't do that. I mean, you could certainly try it. There's nothing wrong with it. It's just I may not get. I want to try and be as efficient as possible with this example. You know, it's a good exercise to try on your own. But, you know, if I did this, you know, and I did it in the XY plane, that would mean that z is equal to 0. And if I go through that, well, if this is 0, I'm gonna get the same expression up here, just in terms of a different variable. So that's not gonna really help me. But it's gonna, you know, you could try it, certainly try it. But let's look at. I want to try and approach 0, 0, 0. Not just with x equals y, but what if I set all three of them equal to each other? What if I make x equals y, and what if they're all equal to each other? So this line, y equals x equals z, is just the universal line that goes through the origin in all different planes. So this plane, you know, this plane, and this plane right here. So this means they're just all equal to each other. So just try it. So just try that. So if I try that, so they're all equal to each other. So it doesn't matter, you know. So x squared equals, you know, that could equal y squared, it could equal z squared, but I'm just going to keep x as x. I'm going to let y equal to x. So this will be x squared, and z is going to be equal to x as well. So I'll have x. It doesn't matter what variable you have here. They could be x squareds, y squared, z. It doesn't matter. They're all equal to each other. So I'm just going to keep it. I'm going to keep it as x. So I'll have x squared plus x squared plus x squared all over 5x squared plus x squared. And when you go through that, so since I just have x's in here now, and it could have been y, it could have been z, it doesn't matter because they're all equal to each other, right? This is the line I'm considering now. That's still approaching 0, 0, 0. I'm going to have the limit as x approaches 0 of this expression, which is going to be 3x squared all over 5x squared plus x squared. That's 6x squared, which is 3 over 6, which is a half. Ha-ha. That's good, because if I look here, smiley face and frowny face, they're not the same faces. So we did it. We showed that this limit is undefined. I know the trickiest part with these problems is, trying to find a curve or a line to approach the given point, right? That's the trickiest part. But, sometimes sketching a graph kind of wraps your head around it, like what are different ways I can approach this. This might have seemed a little weird the way I did it here, like it was a little out of bounds per se, but you just have to see the main point here. I could get to 0, 0, 0 if they're all the same. That's good enough. Try that. As long as I could get to that point on some curve that I pick, I'm good. Try it until you get two different values, and then you're fine. So to finish this problem, since their limits are different, by approaching 0, 0, 0 in different ways, the limit is undefined. That's it. So, you know, when it comes to limits of these things, it's really not, that's kind of the idea behind it. It's just, you know, plug it in. If you get a value, that's the value of the limit. If you get indeterminate, try different ways to approach that point to get different values, and you've shown the limit is undefined. They're really the only two cases you have to consider. Okay. So what we're going to do now is we're going to start talking about continuity. And this is very similar to single variable continuity. So suppose f at x comma y, so we have a multivariate function. There you go. Is defined on a domain centered at some point a comma b. Don't worry about, you know, all I'm saying here is that this function is defined, you know, starting at some point, it has a domain around it. So provided that's true, come on. We could say f of x comma y is continuous at a comma b if the limit of x comma y approaches ab of my function. So what do we know about continuity? What you expect to get is what you actually get. So if I'm approaching this point of the function and ends up being equal to the function at that point. That's what we mean. It's the same thing, you know, with single variable functions as it is with multivariate functions. We're just considering an extra coordinate or extra two coordinates, just depending if it's x, y, or x comma y comma z. It just depends. But that's basically the idea behind it. So a little example here. A function given by so it's piecewise, x plus 3y over 2x plus 5y, if x comma y is not equal to 2, 1, and 4/9 x comma y is equal to 2, 1. All right. Is f of xy continuous at 2, 1? So you're just applying this definition. All right, so plug in, plug this in, and if they end up, you're taking the limit as this approaches 2, 1, and seeing if it equals the function at 2, 1. All right, so if I take the limit as x comma y approaches 2, 1 of f of xy, well, that equals the limit. I know you don't like, writing this whole thing. I could get a little tedious, but, it is what it is. So if I take the limit, so if I'm approaching 2, 1, that means I'm using the top part, right? Because if I'm approaching it, but I'm not equal to it, and that's what this is saying right here. So I'm taking the limit of this function. That's what we mean by taking the limit. If we're taking the limit as xy approaches 2, 1, that means we're not there yet. So we're getting close to it. So if I take this limit, I plug in 2, 1 here. Well, that's just simple arithmetic. You plug in 2 here, so 2 plus 3 times 1, that's 5. All over 2 times 2, which is 4, plus 5 times 1, which is 9. So I get 5/9. But when I'm at 2, 1, what is my function equal to? It's equal to 4/9. They're not equal, are they? So, however, f at 2, 1 is equal to 4/9. So the limit is approaching 5/9. We're expecting to get 5/9, but we actually get 4/9. So since they're unequal, since the limit of xy is not equal to the function at 2, 1, f is not continuous or discontinuous at 2, 1. It's a pretty, it's very similar to single variable calculus with continuity. Same idea. So when it comes to limits and stuff, that's basically it. What we're going to talk about now, which is everybody's favorite topic, we're going to start looking at partial derivatives. So that's what the next video will be on, is partial derivatives.